Okay, guys, exam on Friday. I will try to put some sample questions online just so you have an idea of the format. Anybody that's had me for C++ already knows the format. I will ask you little questions like write a snippet of code to do this, that, or the other thing. And by snippet, I don't mean a complete functioning C++ program. I just mean one that, like, right there in that little local area kind of makes sense. And that doesn't mean that you have to declare everything in sight. You don't have to declare anything unless the declaration is somehow relevant to the problem. It's really just sketching out a snippet of code to do whatever it is that I'm asking you to do. But again, I'll try to put up some kind of sample set of problems that'll show you what a typical exercise might be on the exam. Jamie, did you have a question?
Yeah, it kind of only applies to me, but I mean, it's going to be like similar to the robots test?
Yeah, exactly. Okay. Yeah. And it'll be designed to be done in 50 minutes. And frankly, it's really, you should think of it more like a long quiz than an actual exam, because I'm mostly just trying to test concepts that you should already be dealing with in your programs and making sure that you are getting some of the concepts internally without having to look at the book or what have you. The self-test questions and the readings that I've given you are definitely fair game, and any skill that that I would have expected you to learn in a program is fair game as well. I will talk more about this on Wednesday, but I just wanted to give you a heads up. Yeah, and we've already sort of started a conversation about when, but Monday sounds fine.
And I think I'll probably finish on schedule.
Okay, got it. So yeah, anybody that has a conflict for Friday, we'll just set up a time. I'll be here Monday. I'm not going out of town, so we can probably do it Monday, even though we have off on Monday. So the infix expression calculator is due Wednesday, midnight. I'll try to get those graded on Thursday, any of them that get in on time, and back to you. And then we will move on. The following week, we will be writing a bitstream class, something that will write bits to files and read bits from files. And to that end, I thought today I would spend a little bit of time talking about bit operations, manipulating bits in bytes. Any questions, Evan?
Now that we've got over recursion, I was wondering if at some point we could learn how the quicksort algorithm works.
Yeah, that's part of this curriculum, but it's not until probably 10th week, 9th, 10th week, something like that. So absolutely. Sorting is a big part of this class. And in fact, probably after we do Huffman compression, we'll start a long discussion of sorting. Yeah.
Are you going to give us your testing program for our infix calculators?
Yeah, if I actually write it in time, sure. Saw how well that worked last time I wrote it and then there was a bug, but I'll try to, yeah. That'll, between now and Wednesday, look for it sometime. But your test, that's actually, I'm not going to be writing a test program for that now that I think about it. But I'll try to give you a list of the things that I'll be putting into your expression calculator. Right. Before, when I was linking to your class, it was easy to write a test program that would just exercise your class. But now, it's not going to be a program so much as it'll be sort of a sequence of inputs that I'm going to do on each of your programs. And I'll try to write that down and get that out to you guys sometime in the next 48. All right. Other questions? Ben?
You had a couple on the assignment sheet for homework 3. There were a couple of requirements like using define for all our things, and I was wondering if.
Yeah, I do care about that.
Okay, is that necessary even if we, I think I talked to in class, in Monday's class or something, about using an array to do that instead.
Describe it.
So I have an array with 6 entries from different characters and then a separate unary minus. But so when an operator is read in, it goes through the array until it finds the character that matches itself and then returns its index and uses that in the table.
And so in other places, somewhere you're going to take that index and you're going to make a decision on how to execute the operator. So if it's a 1, do this. If it's a 2, do this. If it's a 3, do this. I think the larger point that I'm trying to make there is, and people that had me in C++ know that this is to avoid what are called magic numbers. So I don't want to see a large if statement that's comparing to 1 or comparing to 2. I want you to compare to add or compare to subtract, where add is secretly 1 and subtract is secretly 2. And you're referring to these magic numbers by meaningful constants. So that's going to be true in general, and I know even when I'm showing you examples in here, I at times I violate that rule, but a well-written program should rarely, if ever, have a literal character or a literal value in the code. If you're going to be using literal values, literal characters, things like that frequently, a good programmer will take those and define them as constants somewhere and give them meaningful names. For example, I may have done one in here where I was using the peek function to look for an enter character, and I did something like cnpeek equals the \n thing. Even that's not cool. What I should really be doing is at the top of my program do define enter \n and then say cnpeek equals enter. Does everybody see what I'm getting at? It's bad practice to use literals in code. They should be named constants instead.
And then second,
yes.
You have in there that we're supposed to have node.h and then .cdp. Is that only if we use that in our stack class?
Yes. So that was before I made the concession to you guys that you could use the STL, the STL stack.
But even if we're not.
Oh yeah. I forgot that node. I forgot node was wrapped up in stack now. Yeah, you're right. So that's just a typo. Yeah. When you wrote your stack, node was at the top in a separate class, top of stack.h, I think. Okay. Yeah. Good call. Other questions?
So for the above and beyond, if we're doing sine or cosine or everything, we want to, we peek to see what the first character is. If we use get after that, will it eat the character or the string?
It eats the character. So cn.get will just eat one character at a time, and get will also not skip white space. So if you do a get on a space, it has to work through spaces just like regular visible characters. It's the only time that the invisible characters, white space characters are skipped is when you use the insertion operator, the double less than thing, extraction operator, the double greater than thing. That's the only time that the white space gets skipped. All right, anything else? These are operators. These bitwise operators are things that I'm wagering most of you haven't seen or used yet in class or anywhere in programming. Let me get a new notepad here. This thing used to remember that I liked grid lines, but for some reason it doesn't now. Okay. So there are several operators in C and C++ that allow you to manipulate individual bits in some larger memory location. And I'll summarize them, and then we'll talk about how to accomplish different things using these bitwise operations. So if I have you're familiar with the basic logic operations of and, or, not, and then you may be less familiar with XOR. So and each of these have tables associated with them. I'm not going to do all of them, but here's and 1 1 oops 1 0 1 0. So true and true is the only one that's true, and everything else is false. Or, you know about or, not basically just flips the bit. XOR is a little bit weird. False or false is false, and true or true is true. Or sorry, false XOR false is false. True XOR true is false. So the only way to get true out of an XOR is if the bits are different. 0 1 or 1 0. 0 XOR 1, 1 XOR 0 gives you true. That's X, I think, is exclusive OR, I think is what it stands for. It's not a standard Boolean operator, but it's one that is useful at times. And so it's included in C and C++. But the whole of binary logic really can be done with and, or, and not. It doesn't need XOR, I guess is what I'm saying. All right, bitwise operators. A single ampersand will and. A single vertical bar is or. A tilde is negation or not. And, oh God, caret is XOR. These three guys, so this is a unary, and the rest of these guys are binary operators. Meaning the three binary operators take two arguments and do whatever logical conjunction they're supposed to do. And the not operator takes a single argument and does whatever it's supposed to do. Okay, so and is a pairwise, oops. So, and is a pairwise anding of the bits in its arguments, and it's necessary that the arguments are of the same type. And I think it's even the case that if the arguments have the same, I'd have to test this, and suffice to say, a good practice would dictate that you use arguments of the same type. But I don't think the compiler will yell at you if you try to use arguments of different types. I think it'll just try to wing it and do the best that it can. So it's really important that you understand it, because now that I think about it, I'm gonna do this on arguments of different types. But how does it work? You take let's say you have byte 1, and you AND it with byte 2. And let's say that byte 1 looks like this, 0 1 1 0 0 1 1 0. And let's say byte 2 is 1 0 1 0 1 1 0 1, like that. And then you want to AND these two guys together, B1 and B2. You'll get a new byte that is the pairwise ANDing of each slot. So 0 and 1 is 0, 0, 1, 0, 0, 1, 0, 0. So B1 and B2 gives you that result. Does everybody see how it works? Despite the fact that my columns don't quite line up. Okay. And OR is similar. So OR is a pairwise ORing. You might be able to guess what this does. Takes every bit and flips it. So 0, 0, 1, 0, 1, 1, 0, 0 turns into 1, 1, 0, 1, 0, 0, 1, 1. Like that. Convenient. Definitely convenient. And then XOR, the caret operator, does a pairwise XORing. Okay. So, those are the bit operations that we have for comparing bits and so forth. Let's talk about one more important operation, and that's bit shifting. Woo. So there are bit shift operators, and they look a lot like the insertion and extraction operators. In fact, they're overloaded operators in default C++. The double less than sign is a left shift, so you could put a byte in here and an integer here, and it will left shift the bytes, sorry, the bits in B1, or in B, let's call it B here, in B by an amount n. All right.
Does that wrap?
Yes, so let's talk about how this works. Let's talk about left shift. So bits are lost off of the left end. And zeros are padded on the right end. So if any information that you shift off the left side is lost forever. You never get it back. And there's what's added on the right end is just zeros. So if I shift left by one position, I get an extra 0 here, and I lose whatever fell off the end out there. When you shift to the left, so let's talk about a byte here, 1 0 1 0 1 1 1 0. So there's a byte, and let's say we want to shift it to the left by 1. The new byte is going to look like this: 0 1 0 1 1 1 0 0. Okay? And the bit that fell off the left end is gone forever. You can never tell whether that was a 1 or a 0 after you do this. You could clear a byte by shifting it left 8, and that would set everything to 0. There are better ways to set it to 0, but that would do it. Shift a byte by 8, and it'll clear it. Okay, left shifting is actually pretty reliable, pretty steady. Let's talk about right shifting. So this, I just want to label this as the left shift. Right shifting essentially behaves the same. There's one little caveat. Right shifting here. The default behavior for right shifting is to pad by the most significant bit. So if the most significant bit of the thing that you're shifting to the right is a 1, then you'll pad by 1s. If it's 0, you'll pad by 0s. And I don't know why they did that. I'm sure there's some great application in computer science that just makes your life so easy if you pad by the most significant bit. So right shifting is padded by the most significant bit. A lot of times you don't know what the most significant bit is. How many of you guys have played around with C and C negative 0? Any of you guys? They're actually, like when you're playing around with floats and doubles, you can have positive 0 and negative 0. And it's part of the IEEE standard for floats to have positive zeros and negative zeros. Don't ask me, Alex. I have no idea why anybody would want to do that. But that can mess you up when you're shifting bits to the right. If you have a negative 0 and you don't know it, and you start shifting it to the right, the minus sign is actually the most significant bit. And so you start padding by 1s. It's a deadly little bug if you... I have not experienced it, but I've talked to people who have experienced that and not known that right shifting is padded by the most significant bit. The way around this, and the only reason I even talk about this is not something that we're going to run into in this class. The reason I talk about this is if you use an unsigned data type, are padded by 0. When right shifting. Even if you do. That's just something you have to know. So you can control the padding on a right shift by making your variables unsigned. And so you're going to see us doing that when we're doing the Huffman compression. You're going to see us using things called unsigned characters. And the reason I'm talking about this is because the first thing people ask me when I start declaring things as unsigned characters is, why are you declaring unsigned characters? And it's to control the right shifting of characters that we're going to do. So the characters are still just characters. They behave exactly the same. Unsigned characters behave exactly the same as regular characters. It's just that in the weird situation where the character has a 1 in its most significant slot, the 2 to the 7th slot, that right shift will still be 0 padded. It's all in the details, I know.
What is the minus sign?
I'm sorry?
What is the minus sign?
Well, in a 32-bit float, it's 2 to the 31. Yeah, it just happens to be in the most significant position. And I think it's all of this stuff is by design to give programmers control over padding in this particular case. But it's really subtle, and if you don't know about it, it can introduce some bugs that are just darn near impossible to track down. And the other thing you run into is there are certain compilers out there that don't really respect these rules.
Awesome.
Yeah, isn't that awesome? Because it's such a subtle rule and so rarely used, it's a bug that often goes undetected in new compilers. All right, let's talk about more fun stuff here than this. what I'd like to do is use these new operations that we've just summarized to set a bit. Actually, I'm going to start with reading a bit. I'd like to read a bit. I'd like to read a bit from some pre-existing variable. In fact, I want to read I want to answer this question. What's the value of the bit at bitpause? So bitpause is a shorthand that we'll use to indicate the bit position. And bit position is, for a byte, the valid bit positions are going to go from 0 to 7. So the 0-bit position is the least significant bit, and the 7-bit position is the most significant bit. What do I mean by that? Let's look at a byte here. Remember how these things work? You have, this is the 2 to the 0 slot, 2 to the 1, all the way up to 2 to the 7. Should ring a bell, binary expansions, yada, yada, yada. Okay. We don't really know internally how these bytes are being represented, and it's not really important as long as we're consistent in how we use them. But the way I choose to write my bits is the same way that I choose to write my regular old decimal numbers. The least significant digit is on the right, the most significant digit is on the left. Right? And that's perfectly consistent with the numbers that we use every day. The 0 through 7 refer to the exponents on the base, 2 to the 0, 2 to the first, 2 to the second, etc. And if I have values in here like 1, 0, 1, 1, 0, 1, 0, 1, I can figure out the corresponding decimal or the corresponding integer just by taking 1 times 2 to the 0 plus 0 times 2 to the first plus 1 times 2 to the second, etc. And then just add those things up. So my question is, if I have this pre-existing byte of data, can I figure out, say, what that one is? What's that bit? All right. Question, comment? Oh yeah, what?
Maintains the order of magnitude. There's somehow the magnitude of your byte is important by shifting when it doesn't change the order of magnitude.
It certainly would be helpful if you needed that to happen. Yeah. It could also maintain the sign, S-I-G-N, of whatever you're dealing with. So you want to shift it, but you don't want to change the sign. Yeah, you could, yeah, okay. Let's look at the character A. So I'm going to declare a variable and I'm going to assign to it the character A. Does anybody remember what the ASCII code for A is?
168.
I was going to say that would truly admit you to the geek elite.
I want to say it's like 65.
A lot of people with computers.
I was just looking at this earlier
All the
today.
numbers.
Or I guess
No, it's not. It starts out with a bunch of different. No, yeah.
Yeah, it starts out with
I think it's 97.
97 is
Lowercase, yeah, and that's the one that I have here. So 97. Heck, I wish we had. Oh, I might still have the program, but I'm not logged in. Remember that program we did on Friday? Was it? Yeah. We can actually see what the binary representation of this thing is. Let's.
Is it still going to be vertical though?
That's all right.
God, not. I can't even read it.
It's in phase 10 right now still.
Oh, thank you. Which one is the least significant?
The one at the bottom.
The one at the bottom?
Or did we flip it? In that,
We flipped it, but that has the it after the say out, so I think that's in the right order.
97 minus 1 is 96, which is...
There's something wrong with this because there's only 8 bits. I mean, only 7 bits here.
It doesn't pad the way it's set up.
Yeah, good point. Okay, so it's 011 00001. Read it from top to bottom, but there should be a 0 in there. So let's write that down somewhere. So there's the base 2 representation. So what I'd like to do is be able to go to, I'd like to write a little program that goes to any particular bit position and pulls out the correct bit value. So I'm going to get myself, this is a character, I'm going to get myself an unsigned character.
what is an unsigned character even achieve?
Ranges it from 0 to 55 to -1 to
Okay, yeah.
But mostly what I care about is the padding. Okay.
I explained this so that no one asks why.
I'm asking you.
Okay, I'm going to declare an unsigned character called mask, and I'm going to set it equal to 1. What does that byte look like?
0, 0, 0, 0.
Yes. I don't know where I'm putting the 2. I'll put it there. So that looks like that guy. Just in your head, can you think of how I might use these 2 guys, the unsigned character mask, all the bit operators I have at my disposal, and the character C to figure out what, the 4th bit is?
Left shifted by your bit position and then and then if there's a 1 left over in your result, then there was a 1 there originally. If there's a 0, then there's a 0.
You mean the right shift.
Right, sure.
I had left shift.
Then left shift.
Yeah. So let's build this up. I'm going to take a left shift.
We're shifting the mask, not the.
Yes.
Oh.
I don't want to futz with C.
All right, well,
I don't want to damage C in any way. So I'm gonna move the mask. Let's move it over to 4 positions. So that does this: 1, 2, 3, 4. So that puts it right there. Okay, and then Luke's suggestion is that we AND this with C. So we have 0 padding when we slide that thing over. So there's zeros everywhere in the mask except for in slot 4, bit position 4. Now when you AND that with the other guys, what's special about AND is if there's a 0 in either the top or the bottom, the whole thing is 0. Or conversely, or maybe not conversely, but if there's a 1 in both slots, I'm going to get a 1. So when I do this mask, If there's a 1 in the 4 slot of the character, I'm going to get all zeros and a 1 in the 4 slot as a result. If there's a 0 in the 4 slot, I'm going to get all zeros.
So AND is a binary operator that returns a character.
In this case, it will return. Hold on for a second.
Isn't it return a bool?
No. I'm just trying to think about which one it does return. Which one would it make sense to return? I think it might return the larger of the 2 data types that it's dealing with.
Oh, okay. So the idea is you could do this with 2 arrays.
Yeah, but that's an excellent question and one I will check on. What is it going to return? In my case, it's not super important, but I think that's an excellent question. So everybody sees how this kind of works. If there's a 1 in the 4th slot, I'm going to get a 1 in the 4th slot of the result. And if there's a 0 in the 4th slot, I'm going to get zeros everywhere. How do I know whether, based on this expression, how do I know whether I have a bit 1 at the 4th slot of C or a bit 0 at the 4th slot of C? If it's equal to 0, then it was 0. And if it's not, then it was 1. Why would it work if I checked to see if it was 0 or 1? Why not?
Well, you might get 2 to the 4th.
Depending on the shift, it's going to be 2 to the 4th, right? In this case, it's going to be 2 to the bit pos. And an easy way around that is to just test for non-zero. If it's non-zero, then there was a bit there. The bit was set there. So you can do something like if this guy equals 0, then bit equals 0, else bit equals 1. Where bit is the answer that we were seeking, right? What is the bit value at the 4th position of the character C? This will get it for you. Okay, so that's reading a character. Did I make? Yes, that's reading a bit.
Does bit shifting actually change the values of the operands? Like when we do mask +4 there, does that actually make mask?
No, it
value
returns.
change? It returns.
Right, it returns a byte that's mask shifted by 4 to the left. Exactly. So mask is undamaged. C is undamaged.
Gotcha.
It's all the return values that you want. Yes, Jamie.
Is there a way of damaging it?
Sure.
You can set it equal to this.
Absolutely. I can do mask equals mask shift 4.
Okay.
And that'll overwrite. Yeah. Okay. That's reading. Let's talk about writing. Actually, why don't I write a little... it's one thing to see the notes. Let's actually do it here. So let's do reading. Let's do this right here. So if C and mask 0. Sorry, mask I equals 0. Bit equals 0. Else bit equals 1. Cout bit. I think this is going to do the wrong order, but let's just get it squared away and then we'll fix the order. That didn't work. Okay, no, that's not it. We can try that. Let me just think it through here. So I get mask, shift it by I, and it with C. If that's 0, then the bit was 0. Otherwise, the bit's 1, and then I want to see the bit. I can't imagine what could possibly be wrong with this. Oh, there we go. Yeah, so it was a precedence issue. And this guy is backwards, so we could fix this simply by putting something like 7 minus I in here. And that gives you A in all of its binary glory. And I guess what's interesting about this is that you're literally going down onto the hardware and you're looking at the bits. And that's something that you couldn't do before today. Or some of you couldn't do before today, possibly.
You're not looking at the bits. Well, I guess you are. But it's mostly just trace.
Well, I don't know. I'm not sure what I think we're struggling with semantics here, but we're basically able to work with variables at the bit level now, whatever that means. So maybe going down to the hardware is a bit of an exaggeration on my part, but we are able to take arbitrary values. For example, I can go, and this might be slightly more interesting. Let's get a double. I'm going to get a float just to be careful. Float x equals, I don't know.
You can do size of I less than, or sorry, I less than size of.
Yeah.
Times 8.
So I'll put, some random float. In fact, I'll put a minus sign in there too.
You gotta fix the left shift. 31 minus 10.
And we can actually see what the bits of this float look like.
31.
Okay, that should run all the way across and show us the most to least significant. Yeah, so it doesn't. What is float? Is it 4 bytes? I thought float was 4 bytes.
No, I think float's actually. Ooh.
Well, I can try double. I'm pretty sure double is 8, and so that's not going to work either.
There's no way for this to, and the biggest
Yeah.
would be like,
So I'm not going to be able to make this work right now.
It has
Float is 4?
sig fig.
Yeah.
well, this, right, but you still need a certain number of digits. You need 8 digits, and 2 bytes doesn't store 8 digits in base 10.
In principle, I could get this to work. I'm not, I'll work on it later because I want to move on to the more interesting issue of writing bits.
Because your mask was an unsigned character instead of an unsigned.
We could try an that's an interesting comment too. We could try to make the mask.
Math.
Yeah, because the mask is not big enough right now, and I wasn't sure what the shift would do, but yeah, let's try an unsigned double.
Can you do hex literal C++?
Does unsigned double one create a double with one in the least significant?
Yeah.
It does.
Invalid operands of type double and int to binary. Oh, this is still an int. Yeah, it doesn't like that. Yeah. Anyway. Mostly it was trying to illustrate, but not getting anywhere. I'll figure it out. Let's talk about writing a bit to a specific location. So, given what we have, let's just stick with the character C. And let's say we want to set bit pause to 1. Given what we know, and again, using a mask or not, as the case may be, ideas?
Do a mask as before, left shifted, set the OR of the result of the input
Back
value
out to the
input value.
Okay, so yeah, the tall bar is an OR, and the short bar is a 1. Think about what happens there. So you've got a 1, which is just a bunch of zeros and then a 1 in the least significant slot. The left shift by bit pause moves that 1 to the correct position. Now you're going to OR it with whatever's sitting in C.
And 1 is our mask, right?
You're going to OR it with whatever's sitting in C. That's going to spit out, essentially there's zeros everywhere in this shifted, in the 1 that's shifted. It's got zeros everywhere except in this 1 slot. All those zeros, when you OR them with whatever's in C, it's going to leave C unperturbed. But the 1, if there's a 0 in C, is going to turn it into a 1. And if there's a 1 in C, it's going to turn it into a 1. Because that's how OR works. And then take that result and overwrite C.
So then if you wanted to say flip the bit at bit position, you could use the exclusive one. Wouldn't that work?
I just was thinking that I think you do it not on the mask and then.
Well, if you just do the exclusive OR, oh no.
Well,
Oh yeah, because all the
only
ones
one
would be
position.
preserved in all the other positions, and then if there were a 1 there, it would give you a 0 if there weren't.
Yeah, that's actually right. That's right.
But this actually gets me to the other side of this thing. What if we want to set bit pause to 0? Say again? You're on the right track. At least you're on the track that I used.
You can not the left shifted value and then do it and.
Right. And, sorry, thank you. Okay, think about this now. You start out with your nice friendly 1. It's all zeros, and then there's a 1 in the least significant position. You shift it, you knot it. All the 1s become zeros, all the zeros become 1s. Now you're going to AND. Sorry, are we ANDing? All those 1s that you've introduced with the knot, they're very friendly to the original byte, right? If there's a 0, it stays a 0. If there's a 1, it stays a 1. Now you've got a 0 sitting in the slot that you're interested in, and you're ANDing it with whatever's up above. When you AND, it's going to turn it into 0, no matter what. That sets that bit position to 0. The bit at that bit position to 0. Jamie.
I mean, this is kind of unrelated, but if you do a bitwise AND in an if statement, like how are Booleans stored in at the byte level?
They're a byte.
So would it be? Is it just like a 1 in the last slot or a 0?
The way Booleans are used in C and C++ is 0 is false and anything else is true.
Oh.
But typically, like if you use a literal true,
right,
you're probably setting the least significant bit.
And so there wouldn't really be a way of doing an if statement with a bitwise AND as opposed to just a regular operator double AND.
I don't see why not. I mean, this is commonly used for setting flags and so forth.
Okay.
You know, so if you have like 8 Boolean things that you want to keep track of, you can do it in 1 byte by using these bitwise operations. Yeah. So if you're just careful, you know what you're doing. Yeah.
Since that's a left shift, isn't it inserting more zeros?
It is. So it takes the 1 and it moves it to the right location, and there's zeros all around it.
Oh, and then does
And then I knot.
Oh, okay.
Yep. But you can see why it's really important to know what the padding is. All right, I'll leave it at that, and Wednesday we'll talk a little bit about review stuff, and maybe we'll get into Huffman codes. Probably not, though.
What is that used for? Huffman codes.
Pretty much every compression algorithm on the planet uses Huffman at some point.
Data,
Yeah.
text.
Yep.